Hello everyone. So in the previous sessions we have been discussing about the naive Bayes and then we coded the naive Bayes from scratch. Now we'll see the overfitting and underfitting in naive Bayes. So what are the possibilities where the model can overfit and where the model can underfit? We have to understand this. So usually we read under the heading of bias variance trade-off. So we'll see overfitting and underfitting. Overfitting and underfitting in naive Bayes. Okay. First, let me again just sort of revise you what overfitting means and what underfitting means so that everybody is on the same page. So what is the meaning of overfitting? So overfitting basically occurs when a model tries to learn the data too well. So it tries to learn the complexity and tries to learn the noise and irrelevant patterns. So basically it tries really hard to learn everything that is in there. And this basically results in what's called as poor generalization. So basically it learns noise also. So it learns irrelevant patterns. Irrelevant. So I'm really bad at spelling, so bear with me. Irrelevant patterns. Okay. So because of these things, there is this poor generalization. So what is the meaning of generalization? That's a big task in machine learning. So you have to generalize well. So I usually give the example of Nokia phones. So when they trained their model on European people, so it was unable to detect the people from African countries because the distribution was different. Okay, and the thing here is that that model was not very well generalized. So overfitting means when your model tries really hard. So it memorizes sort of data. So if you are given data like this, so you have data like this. So everybody can understand this is some sort of like non-linear function. And if I tell you fit the model, you'll probably fit model like this. Okay, this is like good generalization. But sometimes what your model does is to get every point right. So maybe some points are here, some point is here, so some point is here. To get your point right, your model will be like this. So it'll overfit it. It'll try to overfit. Okay, but you know that this is overfitting. When you give the test, it will perform really bad. So this is what overfitting means. Okay, so what is underfitting? Underfitting means your model does not do anything. It gives random results. Okay, that's the meaning of underfitting. Again, in these things, the poor generalization is there. Now I hope that you understood what is the meaning of overfitting, underfitting. We have seen this overfitting, underfitting in detail in k-nearest neighbor algorithm. Okay, now we'll see what are the cases where the overfitting and underfitting can happen in naive Bayes. The first thing where overfitting can happen is, this is also a generic criteria. Also overfitting can happen when you have very small training set, small training data. Okay, so when training data is relatively small, so what happens, the model may capture this noise, or maybe some patterns will be there and they are not very much prominent patterns, and it will still capture them, and it will lead to the overfitting. Okay, so this thing can be there. So it's better to have really good data. It's not if you only had 2-3 points to sort of train the model, so obviously it will overfit these 2-3 points. So it's better to have a good balance of data. So do not have very less points, so have around hundreds and thousands of points, so that you basically learn the patterns and you try to discard the noise and discard the irrelevant patterns. Okay, that's the first thing, like if you have small data. And then if you do not if there is a high feature dependence, so dependence basically means, so does, as we assume that there is feature independence in here, but if there is dependence in the feature, so what will it try to do? If you capture, now it tries to capture everything. Okay, now it will really hard to try. Okay, now features, every feature was independent that we assume, but here there is a dependence in the features. Now you will see if you train it very hard, so what will happen is it will try to capture the patterns, which is basically noise. So here you will see if there is lack of this feature independent assumptions. If this feature dependence, I can say independence, feature independence is not followed. If it is not followed, again we can have the case of overfitting. Okay, and we can also underfit the model if we do not model it well. But one of the most important thing is that smoothing factor, because we know that in case of naive Bayes, what we calculate is probability of class y given some document w given some x. So x here contains words w1 w2 till wd. This is what we want to compute. Okay, and this is proportional to probability, class probability and class prior, and pi j goes from 1 to d, probability of wj given yi. So this is basically what we compute. So here, if you know how to compute this, yesterday we had a detailed discussion on this. So this probability of wj given yi, how it is computed, is equal to count of word j word in ith class. So take class I and see how many times this word j occurs in all these documents which have label yi, and then divide it by the n of j. N of j means number of total words in that yi class. And then we added some smoothing factor, this alpha, and here we added some k alpha. So k, here I said this can be number of classes, as this can be vocabulary size. It basically depends, and alpha here is a smoothing factor. So let's see now what will happen if we do not have this alpha. Okay, what will be the effect of this alpha? Let's say if alpha is 0. So what will happen if alpha is 0? That time, you know that I have told you that if there is a new word which was not in the training, which was in the which came up in the testing, then you will get probability of 0, because now this alpha is not there and count will be 0. This whole term will become 0. 0 divided by anything is 0. Now probabilities are becoming 0 because of this alpha being 0. So there will be 0 probability. 0 probability problem will be there. So what has this to do with something with underfitting or overfitting? So what will happen because of this? Let's suppose what will happen because of this is, so alpha is 0. So if let's suppose I have a very rare word, so that word only occurred 2 times. So 2 times out of, let's suppose, thousands of words. Okay. Now if I change this, so what is basically meaning of this overfitting? So overfitting means if your model is very sensitive towards data change. So if you change a slight data in the model, so your model performs really bad. Okay, it performs really good on testing. So that's why it's called overfitting. It tries really hard on the testing data. But if you change a slight change of data, the model, whole of the model crumbles. That's the meaning of, like a little meaning of overfitting. So model changes drastically. If there is a slight change in the data. Okay. So what I'm telling is overfitting basically means that model is trying so hard on training data, but if you change the data slightly, so what will happen is your model won't be able to generalize. It will perform poorly. So from that, if alpha is 0, now I'm saying there are very rare words. Let's suppose there is a word something like floxinoxynilipilification. It's a really rare word which might not occur in like many of the documents. So if you have 1,000 of these words, and out of these only 2 times some peculiar word occurred, so that 2 by 1,000 is its probability when you sort of compute its likelihood. So now if you sort of remove this word, if you sort of remove the word, so what will happen? 0 by 1,000. Okay, and this will have a drastic change on the model. So now probability became 0. If you sort of change a bit of data, so you just removed that email which contained, let's suppose, this word 2 times. So you removed that email from the now, and now you got 0 probability. Now you saw that there is this problem. So if alpha is equal to 0, so there is no smoothing. So when there is no smoothing, your model is very sensitive to these things. So when you make a little model change, when there is a slight change, so even if this word was rare, now if you somehow remove that mail, you removed just one email in which this rare word occurred. Okay, now whole of your model will not perform good. Is this clear? Is this clear? Yes, so this is called, like, these models are called as high variance models. So they have really high variance. Variance means a little bit of variety. We'll see it mathematically. We have had a discussion on this variance and bias trade-off. So we'll keep on revisiting these things. So what I'm saying is, if your model changes drastically, and if you are making a slight change in the training data, so because of that, what will happen is you will always see that this overfitting has been done, because here you have an email which contains some rare words. So 2 by 1,000 was the probability, but when you remove that email, now you see the probability shrink down to 0, and there you see this. There is a problem that model should not drastically change by just removing one email. So here we have underfitted the case. Okay, now when will overfitting happen? Okay, what are the case of overfitting? So first we saw some differences, like small training data will be there, it will overfit, and then feature independence assumption is not, for example, followed. I can write feature independence is not followed. So if this is not followed, again there's a chance of overfitting. Then we saw alpha also has an effect on overfitting. Okay, same we'll see for the underfitting. In whole the machine learning, basically, why am I teaching it for all algorithms, this overfitting and underfitting? Because there is a fight between the underfitting, and you have to get the best fit model. Your model should not be underfit, or it should not be overfit. It should be a best fit, or at least like average fit, so that it does not fall. Let's suppose you made a spam filter and you claimed the accuracy to be 100%. That's the you solve the case of you solve the problem of spam filter. But in reality, when it was deployed and tested, it did not give the 100% accuracy, and then you can heavily penalized on that. Let's suppose if companies made such claims, and then in the production, when they have the system in production, and they can be heavily penalized based on their assumptions. Okay, if they claim something, so you have to be really careful whenever you say this. That's one of the reasons why I'm focusing so much on this overfitting and underfitting, because there is always this feud, there's always this fight of getting a good model, which should not be overfit and which should not be underfit. Again, what is underfitting? So underfitting is basically when model is unable to underlie any it does not capture pattern, does not capture any pattern, basically gives results as good as random. If this is some random classifier, you can even see the videos on Canon. We have discussed this underfitting in detail there. So what is the meaning of that? So slowly and slowly we'll see these terms in the different lights also. Okay, so what will have how will the underfitting happen? So if there is not sufficient features, so first thing is, if features are not sufficient, features are not sufficient. So what I mean by that if your whole email, let's suppose all the emails contain only one, two words, so then lack of this features will basically give less discriminative power to the model. So because of that, so the problem will happen. So features won't be much there, so we won't be able to learn any pattern. So after all, what will happen is, so your model will perform as good as random. Second thing is, if your structure, if your features, like they do not like here in the first case we said that they do not follow this assumption. So here strict feature independence assumption is, while naive Bayes, because it naive Bayes assumes that the classifier in the classifier we assume that features are independent. So if this assumption may not hold basically in practice, so especially when we deal with the complex data, so if the data is complex, that basically is not always followed. So in here the feature here exhibits very strong dependency or very strong correlations. Okay, so if they are very strong dependencies, that time also this model may underfit, because it might not be able to learn this. Okay, it won't be able to learn all the complex dependencies that we have. So in this also we can have underfitting. So in the same case, so feature independence is not followed. So here maybe there is some dependency, but it is not strict. There is dependency, and for all the features not followed, so we will have overfitting, because it will try to capture these features. But here if you see this, in the second case, if there is a strong dependency in all the features and there is complex patterns that we have, but it cannot capture this. Okay, so because of this it may happen, so underfitting may happen. And then also alpha has an effect, the smoothing factor. So smoothing factor also has an effect. Okay, what is the effect of that? We'll see. So again, taking this thing back, so this is what we have to compute basically. So this is the thing. So if you see it over here, so this is the thing that we have to compute. So now if this alpha is too high, now if you make this alpha too high, okay, so this alpha is very, very high. So what will happen? This alpha is high, okay, and this alpha, this is also very high, because this term, because of this, will become high. So these things will have very less to contribute towards this whole of this fraction. So what will happen is, let's suppose this k is equal to, let's suppose for binary classification we'll take this k is equal to, but yesterday we took k is equal to size of vocabulary. It depends how you take. Let's suppose we'll take 2. So just for the demonstration purposes. So if alpha is, let's suppose 10 to the power 4. Okay, count of the words will be maximum, it will be 200 or 300. So 200 plus 10 to the power 4 divided by total word count will be, let's suppose 1000, and plus this will be again 2 multiplied by 10 to the power 4. Okay, if you see these numbers 210, this can be easily written, this nearly equal to 1 by 2. Okay, so for all the words, so for all of these words, for all the words, because if you see that we have probability of w1 given this class yi multiplied by probability of w2 given this class yi, and so on till probability of wd word d given this yi. So here if you see that if we increase the alpha, so this will nearly become 1 by 2. So this will also become 1 by 2. So this will also become 1 by 2. Everything will become 1 by 2. Okay, so nearly everything will be equal then, because we are incrementing this alpha. So if you see in the formulation, so what will happen? If you see in the formulation, we have probability of yi given some email given some x, that was equal, that was proportional to probability of yi class prior is multiplied by pi of I is equal to 1 to d probability of w, we'll write j divided given that yi. So this part will become equal. Now for, let's suppose this is for class, this can be class 1 and class 2. So we can have this equal to class 1, we'll compute this for class 1. Okay, and then we can compute the whole thing for class 2 also. Probability of yi is equal to class 0 given x is proportional to probability of yi is equal to 0, and pi of j is equal to 1 to d probability of wj given yi is equal to 0. So now this part, if you see, this portion will become equal in both of these because of the alpha being greater. Okay, so this part will have no effect basically now. So everything befalls on this part. Now the classifier will basically get biased towards the majority class. It will get biased towards the majority class. While it get biased towards majority class, let's suppose the class prior was 0.9 here, and here the class prior was 0.1. Okay, these are the class priors given to us because we have alpha now increased so high that this and this term became nearly equal. So these two terms nearly became equal. So what will happen because of this is now whole of the this probability will be posterior will be calculated based on the class priors. Now you see that this probability has 9 times. So this always will be greater. So our model will be telling for all the point, it will say all the points of our majority class. Okay, how many of you understood this? So when we increase the alpha, so what will happen? So whole of this basically, whole of this will get, so they'll have the same effect in both the classes. If here we are dealing with binary classification, so if you have k classes, this factor, this likelihood will be equal for all the classes. So then what is the deciding factor? The deciding factor is the class prior. So now class prior, if there is some imbalance in the data or something like that, so whole of this will depend on this now. Okay, or even if we have balanced data, then it will be 0.5, it will be 0.5. Our classifier is as good as random. So it is better to choose this alpha very carefully because of alpha you can have overfit and you can have underfit. That's the reason you should choose the alpha very carefully. How many of you understood this?
Yes, sir.
Zakir?
Yes, sir.
So because of this alpha, you can have overfitting and you can also have underfitting. So you have to choose this alpha very carefully. That's why sometimes alpha is chosen as 1. That's why I told you this smoothing, or we said this is called as additive smoothing, because we most of the times, most of the libraries, they add 1 to it. Okay. So that's how to, now this alpha is called a hyperparameter, as you know that this is hyperparameter. You have to set it so that you do not overfit or you do not underfit, because it'll like drastically change the things. So smoothing basically change the things. So let's suppose I'll give you one more example how smoothing may affect. Let's suppose you have 2 words. So you have very rare emails. So in which we have 2 divided by some, let's suppose 2 divided by 100, and then you have some other word 8 which occurs 8 times, 8 divided by 100. So when you add this alpha, so let's suppose you add this alpha, and because you add the same alpha over here also, so this is plus k alpha and something. So if you add alpha over here, so then you will see that this will have more percentage gain. Okay, so this alpha basically does a sort of imbalance, creates an imbalance. Why? Because if you add alpha over here, the same alpha you add over here, because these points were already more. Okay, now you add a little alpha over here, so percentage gain will be more over here. So percentage gain on this will be more, because again this numerator was constant, some sort of this was constant, but if you see that overall, you will see that this will become more. So here the percentage gain will be more. So that's why you have to choose this alpha carefully. Sometimes a hack around this is people choose different alphas for these, but this is like why it's called a hack, because this is a temporary solution. So the best part is that you see the data, and based on that you can choose alpha. And usually I told you that alpha is basically most of the times chosen as alpha is equal to 1. So we choose this alpha is equal to 1. Right? And these are called hyperparameters because you are the one who is responsible for choosing this. So we have when alpha is equal to 0, so what happens? We have these numbers become basically very large, and some slight change in those emails may disturb the whole model. So we are saying that the model is overfitting if this alpha is equal to 0. So overfit basically means high bias. So we have very high biased model. Okay, so then when alpha is very large, so it's very large, so what will happen is underfitting may happen. Underfitting, it does not learn anything. Okay, underfitting means high variance. So underfitting basically means high bias, and this is high variance. So variance means variety is more. Okay, high bias models basically mean the model which are underfit. So that's why it's called a bias variance trade-off. Bias variance trade-off. Okay, because you have to adjust bias and variance such that your model is not overfit, is not underfit. So high bias model basically means underfitting, and high variance basically means overfitting. Okay, so alpha is 0, so in terms of naive Bayes, you will see that overfitting will happen. If alpha is very large, so you will see that underfitting will happen. So you have to choose alpha very carefully. So usually we take alpha is equal to 1. Okay, that's the standard value. If you see different libraries implementing this smoothing, so you will see that in these libraries alpha is taken as 1. I hope that this is clear. So we saw the underfitting and overfitting of naive Bayes. Is it clear?
Yes, sir.
Okay. So what is the next term that I want you to know is called as interpretability. Okay. So interpretability and explainability, and sometimes interpretability and explainability. Explainability. And with that, we also compute the feature importance. Feature importance. So these are the terms which commonly will be used in every of the algorithms. So I'm using this naive Bayes and seeing so what is the meaning of interpretability and explainability, and what is the meaning of the feature importance. Okay, so naive Bayes basically is an algorithm. So first I'll tell you what's the meaning of this, why is it important. So interpretability and explainability, they are really important in machine learning, because you have to explain something, you have to interpret something. Okay, so if you have your model is doing some decision, so if your model is performing some decision, okay, and you have to tell why is your model performing certain things, why is it doing certain things. Let's suppose you're working in finance, healthcare, it detects cancer for a patient. So interpretability comes into picture. What is interpretability? How do you interpret these things? So how do you interpret the decision? If it's saying the patient has cancer, why is it saying so? Okay, that becomes really important. So if you do not give a, if you do not interpret the, if you cannot interpret the results, so what will happen because of that is maybe it won't go in the deployment. I recently met an IBM employee. He told me that we have a lot of models which perform really good, but they are not interpretable. We cannot interpret the results. Okay, then you can see the AI wars going. Sometimes AI giving like really bad results. Why is it giving? Because these models are not interpretable. You don't know why is it giving certain results. Okay, so we want models which are really interpretable, like particularly in terms of finance, or in terms of medical domain. So you want your model to be interpretable. You want it to you want its result to be interpretable. If it gives some results, you should know the rationale behind those results. Okay, this naive Bayes algorithm is interpretable by nature. Okay, so there are different methods by which you can compute interpretability. In KNN there is something called as forward feature selection, okay, by which you see okay which features are resulting in what. So naive Bayes basically is, so this is inherently interpretable. So why is it so? So before that, let me cover feature importance. Okay, so what is the meaning of feature importance? Which features are more important, as the term says. Okay, and because of this interpretability and feature, if you know sort of these, and now you can build this trust and transparency, because your model might be used in naive Bayes, your model might be used in finance or medical. So there you must give some trust and transparency. And the second thing is you must regulate, you must be compliant with the regulatory bodies. Okay, there you are saying somebody is a fraud, somebody like you claim again is somebody that he's a fraud person, like your model says you should not give a loan to him, and because your model predicted that if you do not give a loan, that that person may file an FIR or lodge something against you, and you will have to basically give the reasons why the model is showing that. If you have no reason, and you can, like, company can be penalized really heavily. So because of these things, and even with debugging and improving the model, if you know why your model is performing in a certain way, you can improve the model also. So because of that, this interpretability and explainability and this feature importance becomes really important. So what is feature importance now? So which feature is more important? Okay, what features are more important related to what class? So I told you that naive Bayes basically naturally is better at these things. If you see what we do compute in naive Bayes, we compute the likelihoods. Okay, so if you have, let's suppose, a word in emails, okay, if you have this word, so you basically compute its likelihood, probability of this word given class 0, and probability of the same word given class 1. You basically compute these likelihoods. Okay, and you will get some numbers over here. These will be the numbers. So now what you will do is you will sort these numbers, let's suppose, in descending order. Okay, you will sort these numbers in descending order. So whichever whichever words are at the top. So let's suppose some word has 0.02 probabilities, and after that we have 0.19 and something like this. So if you have the topmost words are more important. That's what your feature importance says. So here you see that because we are computing the likelihood, so like we have a table like this, each word is given a likelihood with respect to each class. So you can just sort it, and you can see the words which have more probability in a certain class, these words are more important, and these features are more important. Okay, you basically do it. So let's suppose if I even label now, if I'm given, so how is this feature importance making it interpretable? So let's suppose I have been given an email. So this was an email, and I told this email is spam. Okay, if I was told why is it spam, okay, now I can say that because this email contained words like, let's suppose, buy, lottery, and some things like that, and my model says that whenever you have this buy, lottery, so these emails have very high probability of being spam. Okay, and if you consider some mail to be ham, so why is it ham? Because you are saying that this this model says that this by a spam or by, let's suppose, lottery, and these words have very less probability. That's why we can see it from the likelihoods. This is how you can interpret it. Okay, and this interpretability is, it's really important. Okay, so if you see that probability of free given spam, so it will be very high. It will be like nearly, let's suppose, equal to 0 point some 8 or something. So in most of the emails you will see some free spam emails, because they have to target, they have to market the things. So probability of free, and if you see probability of free in non-spam, it's, this still will be there, it will be in the non-spam emails also, but you will see the probability is very less, around 0.1 or something. And similarly, probability of money with respect to spam is very high. Probability of, let's suppose, university with respect to spam may be very low, because sometimes your university may say something, if your university's name is some university or something like that. So these words free, it has free or money or lottery, they have really high probability of being in spam. That's what our likelihood tells us. That's why these models and by the feature importance we can easily say that we have the model can be interpreted. And then in addition to this interpretability, so we can also give the explanation also. So explanation of the model. So if you have a new email, and let's suppose that new email is get free money from this amazing opportunity. Now the naive based classifier will tell, let's suppose we have email get free money from this opportunity, something like this. Okay, if this is a new email, so now our model will basically compute all the probabilities. Okay, and we will be able to explain why we took a certain decision. The first thing is interpretability. Interpretability was how do I interpret the results. Okay, why is it giving the probability high? Because free occurred in many spam emails. So what is explainable? So why this email was, now if it took a certain decision, can you explain your decision? That is explainability. Interpretability means, so how do you interpret the results? So this feature is having an effect, this feature is having. Explainability means if it took a decision, so why is it taking a certain decision? Okay, and now this naive based classifier, as you saw that, this clearly can be seen that this inherently gives us interpretability, gives explainability. That's why it's used as a baseline. So this model is used as a baseline in many natural language processings. So if you have to build a spam filter, if you have to build a sentiment analysis program or something, so maybe you can use complex models, some like in deep learning you can use transform based model, which are really complex. So but first thing you will do is you will use the simplistic model of naive Bayes and check the base. Let's suppose this is giving you accuracy of 95%. If deep learning is giving you accuracy of 96%, you are saying that my baseline model, my simplest model gives 95% accuracy. For 1% I will not use much compute power, because this deep learning model they use really high compute power. So it is better to use this model. Okay, so I understand the points. So here you saw that what is the meaning of interpretability, what is the meaning of explainability, why is it important, and why is naive Bayes inherently explainable and interpretable. Okay, then we'll see does class imbalance has an effect. Does imbalance has an effect on naive Bayes? Because we also saw this in our K-N algorithm. So you have to see if it has imbalance, how will your model react? Because I told you you have to deal with this imbalance. How to deal with this imbalance? We have had a detailed discussion on this. There is a full lecture available that you can see how to deal with the imbalance, up sample, down sample, class weights, and there are a lot of techniques that we have done. Okay, so how to basically does the first thing we have to check is, does imbalance have an effect over the naive Bayes classifier? Okay, because I told you some algorithms inherently do not, or they are not affected by imbalance, but most of the algorithms are. So we'll see does imbalance affect this. So what I'm saying is, if you see this, what we are computing is we are computing posterior. That's probability of yi given some document or given some email. We'll call it x. So this is proportional to prior probability is probability of yi pi of j is equal to 1 to d probability of wj given this yi. So this is what we compute. So even if you see it over here, so let's compute this thing is constant. Let's suppose we are not caring about this thing. Now class priors are there. So this class priors, they are computed based on the number of data points we have. So if you have, let's suppose a bunch of you are 1000 emails, so out of these 1000 emails, 300 emails are spam and 700 emails are ham emails. So you will see that there is a high imbalance in here. Okay, so then this will get affected. So here if you see that this will get probability of 0.7, the other will get probability of 0.1. So this is 0.7 and 0.3. Now you see that this is having an effect. So you have to deal with the imbalance. Okay, so what will happen is, so when there is an imbalance, our classifier will be biased towards majority class. So here you will see that this model cannot deal with imbalance. Inherently it cannot deal with imbalance. We have to deal with imbalance ourselves. So how will we deal? We'll upsample or downsample. We'll use upsampling or downsampling, so that to bring these samples in the certain range. Or one more thing that you can do is, you can basically leave these class pairs. You can leave this in the formulas. You can leave it. Okay, leaving this is equivalent to taking same value for both of these. Okay, if you are leaving this, and if you are leaving probability of yi is equal to 0, you are leaving this also, you are leaving probability of yi is equal to 1 also. In both the classes you are leaving the class prior, so that's equivalent of like not caring, giving it equal probability. So we are saying that all of these are equal probability. Now we are just removing it. So this is one technique. So one technique is upsampling, downsampling. Then you can leave the class priors. So you can leave this class priors, and then you can find some research papers. So there are a lot of research papers which basically deal with this imbalance. So I won't consider this a technique because they are rarely used, very rarely used. There is complex research done which says okay, how to deal with the imbalance and things like that. Okay, so it's better you can maybe use upsampling or downsampling, or maybe you can just drop these class priors, because if model is imbalanced, then our model gets biased towards a majority class. It's better to leave their probabilities in altogether. So it's better, this is the better way. Okay, so this is how the imbalance affects the naive Bayes, and we have seen how to deal with the imbalance. And then we also have, if we have missing values, how to deal with that. Okay, in naive Bayes, how to deal with missing values. If we have naive Bayes, so how to deal with missing values. So here you will see in text classification you won't have missing values. So in text classification, most of the times you don't have missing values. So because you just consider the vocabulary and you construct it by using the text. But if you have these categorical features, so if you have categorical features, so in categorical features, each feature will have some categories, and some of the category may be missing. So let's suppose this is your data set, and this is one feature which is categorical. So for some, let's suppose this data point, the value is missing. There is that NA and not a number or something like that. So how to deal with this? So this is even a generic technique. So let's suppose your categories are A, B, and C, but here there is no category. So what you can do is you can just add one more category. You can say that not a number is n the category. Okay, you can just make it 4 category. That's one of the how to deal with this categorical feature if there is a missing value. And if there is a missing value in this numerical features, so if we have numerical features and there are missing values, we have also had a detailed discussion on this. So how you can do is you can impute the values. There are imputations like you can interpolate, you can take average, or you can take sum. So there are different techniques, or you can use even k nearest neighbors for this. Okay, you can impute the values. And basically what I'm telling you is, so mostly naive Bayes will be used for text classification, so there is no chance of missing values. And then outliers also affect it. So what is an outlier? So outlier basically which does not follow a certain distribution. So let's suppose your samples are of certain distribution and there is a point which is not lying in that distribution. Let's suppose your emails are like this. Okay, they lie in this range, and then one email is like this. This email is an outlier. Okay, so what will this email do? You saw that we deal with if this in the testing phase, so we'll use alpha for this. So we smoothen it out. This basically means you got some words which were not in the training. Okay, they were in the testing. So what do? You use alpha. So if there is an outlier in the training also, if there is an email which is very rare, so what will you do? You probably will leave that email. So if there is a word which occurs less than 2 times, you won't consider that into probability. You won't compute likelihood for that word even. So you will say that I'll leave this word altogether. So this is for training. So in training, what will you do? In naive Bayes, if there is a word which occurs, let's say less than 2, less than 3, which is very rare. Rare basically means outlier. So you'll just leave it in the training. In testing, what do? If you got a very rare word, you use smoothing factor. This is in testing. Okay, so this is how you deal the outliers within this naive Bayes classifier. Because when you are making your classifier, you'll have to deal with all of these things. You'll have to see if there are missing values, is the data imbalance, are there some outliers, and what to do with the data. So because this processing of data is same for everything. So processing of data is same for every algorithm. More or less it's same. Because you have to there are some algorithms in which you have to perform more or less steps, but more or less you will see 80 to 90% of the process is same, because you remove duplicates, you fill these missing values, you deal with the imbalance, you deal with outliers. That's why we are seeing them in perspective of Kane, and we also say how to deal with outliers, how to deal with class imbalances. Here we are also seeing that. I'm just making this discussion very brief so that you got a gist of this. Okay, in every algorithm we have to deal with this. So this pre-processing of data is more or less 80% times the same. Okay, then we'll see why to use this naive Bayes. Okay, why to use naive Bayes. As we saw in Cannon also we saw why to use Cannon. So we saw if the data has a structure, and if we assume that the data is basically a point is same as the nearest points which is have. So okay, if it has a point, if this is a point and its neighbor points are these points, so we'll also call this point as blue point. Why? Because the neighbors are blue. So we consider that if a point is there and its neighbors are of a certain type, the point also belongs to the same neighbors. Okay, this was the assumption in Cannon. Okay, then we also have some assumption in here. So some assumption we did in naive Bayes was that features are independent. The features that we're taking, they're independent, they have no dependency. If you can sort of live with that assumption, if you can see that my features do not depend on each other, so this model will perform better on this. So features are nearly independent. So if such case happens, so then what will happen? Your naive Bayes will perform really good, and this naive Bayes also performs really good on text data. We saw yesterday, we saw that our model was giving 97% accuracy. Still, this is overfitting. Why? Because we have very less data. So we had, I think the data was around 5,000 emails or something. We saw in the previous session that by just using techniques of like some pre-processing, we did lowercase and then we tokenize it and something like that. We have accuracy of 97, but it's an overfit model. Why is it overfit? Because data was less, and we have to also adjust alpha and see what the things that will happen because of alpha. And if you give it more emails, will it be able to generalize well? Okay, you take your spam folders, download all the emails that are in the spam, and whatever model we built yesterday, you can give it to that, and then see how is your model performing. Okay, but I'm saying this performance is really, for naive Bayes, performance is really good when features are nearly independent, because you cannot assume that features will be fully independent. They'll be nearly independent sometimes, and then it also performs good on textual data. And what I have observed in my day-to-day life is that even if features are dependent but not highly dependent, if they are dependent, still this naive Bayes gives reasonable answers. Okay, and one more thing is why will it be used? It will be used where interpretability is important. Okay, if interpretability is really important, I showed like in finance, in healthcare, sometimes interpretability of the model is way important than the performance of the model. Because if you detect that somebody has cancer and he actually did not have cancer, he'll go under this chemotherapy and it will not benefit. And sometimes you may detect that a person does not have cancer, but in reality it may have cancer. Okay, and why does it do that? You must have the results to be interpretable. Why is it performing so if you have a model which is really interpretable, so particularly in finance and this healthcare, it becomes really important to have these models. Okay, so and even sometimes if you have limited data and you want to create a baseline for a baseline of a model, you want to see, okay, my baseline performs this good, if I now use complex model, so what will happen, how much accuracy gain will I get, at least in terms of accuracy, then you can also use this naive Bayes algorithm. Is it clear?
Yes, sir.
So let me. So now what we have seen is we have used naive Bayes for the categorical features. Words basically are categorical features. So we saw that different types of features are there. There are continuous features which take numerical values, like any real number can be there. It can be height of people, and then there are features which are categorical. It may be binary categories, can be 0 or 1. Like if you sit and talk about gender or sex, we have 0 1, male female. Okay, and then if you talk about some other categories, like we solved the problem of that weather prediction, in that we saw sunny, then we saw rainy or something else. So these are categories. So inherently, if you see that naive Bayes classifier is good for categorical features, but you know that we may have continuous features also. So we may have continuous features. So now how to basically handle this naive Bayes, how to use this naive Bayes with respect to this continuous features. So if you have a data set, so you have data set like this. Let's suppose I'm creating a data set. Okay, in that we have these features are continuous. Okay, now the topic would be how to use naive Bayes for numerical features or continuous features. Okay, so numerical basically they take some range of, they take a continuous range of values. So in that, if you see, again coming back to the basics of naive Bayes, we say probability of yi being in class 1 or class 0, given that let's suppose we have feature, we have this feature I feature, then we have x1. Let me write it like in some, this is ith email and one feature, comma, ith email second feature, ith email third feature, something like that. Let's call this j. Okay, this is what we basically want to compute. Okay, we wanted to compute the probability of this, and for whichsoever class this value becomes maximum, so that's why we write argmax of this. Argmax means which for whichever class, for whichever j this value becomes maximum, so that is the answer that we get, that is the j that we get. So here if you see that now these features can basically be have continuous values, or they can have a continuous range of value. They will be numerical features. Now if you previously saw that we have categorical features in there, so this email can be here, xi can be, this is the email that we have, so this will be its xi1 feature, xi2 feature, and so on, xid. these sort of features. Okay, so now what do we want to compute? You basically compute is probability of yi is equal to 1. This is our class prior, and then you multiply it. J is equal to 1 to, I think this is j and this is I am being consistent with the notations now. So this is I to let's suppose d features we have, then we'll write probability of x I j. Okay, this is ith email and this is jth feature given yi is equal to 1. Okay, so our class is y1 is equal to, so here class pairs is easy to compute. You know how to compute the class pairs. So class pairs basically you will take this data. Let's suppose here y label is 1 and here the label is 0. You'll basically count, this is number of classes that are label 1 divided by n1 plus n0. This will give you the probability of yi is equal to 1, and then probability of yi is equal to 0. This will be given by n0 divided by n1 plus n0. Okay, and this is how you compute the class priors. Now the question becomes of this, how to compute this thing. Okay, how to compute the class priors, how to compute this likelihood. Okay, so now what we'll do is we basically assume a distribution. What we say is we say that each of the feature comes from a distribution. Let's suppose I'll take probability of some feature x I j, okay, given it is from class y I is equal to 1. Okay, y basically means positive class. It's from no spam. Okay, this is our no spam class. So what I'll do is I'll first select only this. So from my whole data, I'll select only this one label classes. So this is the label which we'll have, and then we have this feature. So this feature will be there. Okay, so you know that this feature will follow some probability distribution. So what I mean by probability distribution is, so by probability distribution, how are these values distributed? So if you see, there are different probability distributions. We have seen that we can construct PDF and CDF of these functions. So we have also done this in expert data analysis, where we said that for each of the thing. So if you have a random variable, that random variable, if it follows a distribution, we can plot its PDF. So we also saw there a bell curve, Gaussian curve. Okay, we'll see this in detail when we go in depth in the probabilities, but here in nutshell we say that if you have a random variable, if you have, let's suppose a feature is a random variable, if you have a feature and it takes some values, now you know that it will follow some distribution. So if it follows some distribution like this, okay, so let's suppose this value is 6.8, so 6.8 is somewhere around here. Okay, and this distribution is with respect to class 1, because we have fixed class 1, and then we saw what's the distribution of this feature 1 with respect to this class 1. So let's suppose this is the distribution. So now this value is 6.8. So corresponding to that, we can find the probability from this PDF. So this is our PDF, probability density function. So from the probability density function, we can compute the probability of this. So that this is basically equivalent to this. Okay, now you know that the distributions, when we will learn about this Gaussian distribution, this power law distribution, there are a lot of distributions that we have. So from that you will see that for let's suppose Gaussian distribution, there are only two things which in the Gaussian distribution. If you know them, you know the whole Gaussian distribution, and that is mean and variance. So you have this called normal distribution, then the mu and sigma. This is its mean and this is variance. So if this mean basically means what is the central value, and variance basically gives the spread. So if you know these two, you can uniquely construct this distribution. So now this normal distribution has its own formula. Okay, when you just input the 6.8, it will give you the probability. So it will give you this probability. So this over here, where we assume that these features, they follow a certain Gaussian distribution, we call this Gaussian naive Bayes. So Gaussian naive Bayes, what is the assumption here? So the assumption is that features of a certain, let's suppose feature fi, let's suppose ith feature of a certain class follow Gaussian distribution. So what will happen, because of Gaussian, now we have direct formulas to compute the probability. We will use PDF of Gaussian, and there is a formula, and when we'll go into in depth in this Gaussian distribution in the probability, we have just I think scratched the surface when we were doing expert data analysis. I hope that from that lecture you remember that each feature we can plot its distribution by plotting those histograms, and then we'll use KD, we'll use kernel density estimation. We'll smoothen out that curve and we'll get the curve like this. Okay, and then we can also use some other distribution. So if you use some other distribution, we call that accordingly that naive Bayes. So if you have used, let's suppose Bernoulli random variable. So let's suppose in Bernoulli you see that in let's suppose in binomial you say that the values that will be taken will only be 2. Let's suppose word I, probability of word I given some y class yj is equal to 1. So this word can be either present or it can be absent. So it takes only 2 values. So here if you assume that this feature takes only 2 values, so then it will be called as binomial naive Bayes. Okay, and then because we assume something about the data. So that's what I'm saying here. So here my focus is that how, if you have a numerical feature, so assuming that you have numerical features, how do you compute this likelihood? You first fix the label. So among the, when you fix this label, you will compute, let's suppose you have label 1 label, you fix the label 1. So in this label 1, you will compute the PDF, you'll see what is the PDF, and in label 2 you will also compute the same PDF. Let's suppose that PDF is somewhat around here. Okay, so if point was 0.68, let's suppose in label 1 it belonged here, 6.8 is here, so 6.8 may be here in label 2. So here the probability will be this, so here the probability will be this. So you will see among these probabilities which is more, and this belongs to that label, label 1 or label 2, basically class 0 and class 1. Accordingly we'll use that because we'll use PDF. So usually what we assume is, we assume that in Gaussian naive Bayes these features come from a certain Gaussian distribution with certain mean and with certain variance, because in Gaussian distribution you only need two things, you need this mean and you need variance. So we'll assume that this feature, let's suppose feature according to feature I, so feature I, it comes from a normal distribution having this mu of label 1 class 1 and sigma class 1. So this is for when we have this label 1. So if you have label 0 or class 0, so in the, for that feature we'll assume that this comes from some normal distribution having sigma 2 as mean, having mu 2 as mean and sigma 2 as variance. Okay, for label 2, this is a class 0 and this is a class 1. So accordingly this is what we'll form, because this is these two are the parameters by which you can compute the probability of a point in a normal distribution, in a bell curve, and we'll see these things in detail. So the takeaway from here is, if you have these numerical features, what you do is you assume a distribution with respect to classes, with respect to class 1, class 2, class 3, and then you see which among them gives the maximum value. Is it clear?
Yes, sir.
Okay, again to reiterate, when you have numerical feature, what you do, you basically assume a distribution. Usually you assume Gaussian distribution. So in that Gaussian distribution, what you do is you have a certain mean and certain variance, and according to that you compute the value of probabilities. Basically when you fix the class, so this is given class now, and then from PDF you basically compute this. So basically that's how you compute the likelihood. Okay, you assume some fj has a certain distribution in Gaussian with this mean and with this variance, and from that you can easily compute the probability values. Whichever probability is more, that you will assign. Okay, so if this value is 0 or 1, we'll call it Bernoulli naive Bayes, because Bernoulli takes two values. Bernoulli, because Gaussian is basically when this is bell curve, this symmetric curve, when we have curve like this. So Bernoulli is where the values can be two. Bernoulli distribution, we say that in heads and tails we say it follows a Bernoulli distribution. Then whatever we saw previously, it's called as multinomial naive Bayes. Okay, we saw that words can take different values, we saw words can take many values, so we call that as multinomial naive Bayes. Okay, and depending on distribution you can name a different this naive Bayes techniques differently based on the distribution that you are assuming. You can assume that likelihood follows Bernoulli distribution, then you will call it Bernoulli. You can assume that it follows Gaussian distribution, you can call it Gaussian. So this assumption is important. So what assumption you take about the numerical features, and you will call it accordingly. Now what is your homework for this? Your homework will be to see scikit-learn. So in sklearn they have implemented this very nicely. They have implemented this naive Bayes very nicely, and they have this multinomial naive Bayes. I think they have Gaussian naive Bayes implemented also there. So you just import these things, and the data that we have, I'll provide you with this data, and then you just use this sklearn, and then for your testing purpose, then you will be given a full-fledged assignment. And I hope that you understood the naive Bayes concepts, and I don't think there is much to discuss about this. And there will be small tiny concepts which you may find it on your own also, but all in all we have covered all of the naive Bayes in all together, and you can now use it everywhere if you want, and you can use it in your projects and stuff like that.